talking about mass balance without reaction. So what were the two assumptions that we did before so that it will become a simpler way of representing our mass balance equation? So that was mass balance without reaction. So if it's a steady state condition, this is zero. If it's a conservative pollutant, that is where there is no reaction. So the pollutant is not reactant, it's not degrading, it's not producing new materials. So this part here will be zero. So if we are using a conservative pollutant, the R, the rate of reaction, is zero. So if we are using two assumptions here, in our previous example, steady state, it becomes zero. Conservative pollutant using a conservative equals zero here. So what is remaining is only the mass flux in and the mass flux out. So with that, your problem becomes simpler. All right. So now let's go towards a more, a little bit complicated mass balance, because this one now has the reaction. It means that the contaminants or the concentration of the reactants are actually reacting in the solution. So it could degrade or decay, or it can form into new materials. So that's why this is a plus minus here, because decay means reducing. So we can use a negative R. So the reaction rate is decreasing. What I mean is the material concentration is decreasing. So the reaction rate is always positive, all right? The reaction rate is always positive. So when we say reaction rate, is basically the change of concentration over the change of time, all right? So change of concentration, this is R here. I should put the small r here. So R is basically reaction rate, change of concentration over change of time, which is in terms of the units, this is a molar per second. So in terms of molarity, right? Molar per second. It could be also in terms of mass. It could be milligrams or kilograms per second or kilograms per day. So this is the change of concentration. How much is changed based on the time it is in the solution. So this R is based from the kinetics, the chemical reaction called kinetics. All right. So kinetics is basically the study of rates of chemical processes. How long will the reaction occur and what's happening in the reaction? Is that the kinetics of that process? All right. In this case, the R, the reaction rate, is basically related to the concentration, as I mentioned, the change of concentration, right? So this one can be equated as R is equal to negative K C to the raised to the power of N. I will explain to you how we get this equation now for the reaction rate. So K is basically the reaction rate constant. It's a proportionally constant. So this one is how much, the constant is how much the reaction is going on. And it is based on the concentration as well, raised to the power of N, which is the order of reaction. Okay, so I'll give you how did we get this one in the next slide. So let's say, for example, when we do a chemical reaction, we use a reactant, right? And then it goes towards making into a product, right? So there's a reaction, there's a concentration in the reactant. If we have one reactant, then we will get a one product as well in this case, right? So they have different concentration. So let's say that the reactant concentration is A and the product concentration is B. At time zero, at the initial time, let's say the concentration of A is 1 molar, all right? The concentration of 1 molar. So this is still at the reactant stage, the condition. So the product is still, at time zero, is still zero, all right? It's still zero because it's not reacting. So when we do after a few minutes, after a few seconds, let's say at time equals 2 seconds, all right? The reactant has now reacted, okay? Has now degraded and it formed into 0.98 molar now. So it means 0.02 molar was reduced with 0.02 molar. So in these terms, because there are only one reactant, one product here, at time t equals 2 seconds, the product will now gain 0.02 molar, right? Because it's coming from here. From a mass balance point of view, whatever is reduced from here should be on the other side as well to balance the masses. So in this case, this is 0.02 molar for the product. So now based on the rate of reaction equation, the change of concentration over change in time, we can calculate the rate of reaction for the products first. So the change of concentration is basically the final concentration minus the initial concentration over the final time minus the initial time. All right, so in this case, what is the final concentration? So for the product at time 2 equals 2 seconds, the final concentration is 0.02 molar. So we put it there, 0.02 molar, minus the initial concentration of 0. So in this case, it's positive, right? 0.02 minus 0 is 0.02 over the change in time, which is 2 minus 0, so over 2. So if you divide that one, you become 0.01 molar per second. All right? So now we have the reaction rate now. So this is 0.01 molar per second. So let's go towards the reaction rate calculation of the reactant. So now at the reactant, the final concentration is 0.98 molar. All right, so we get here 0.98 minus the initial concentration of 1 over 2 minus 0, which is 2 seconds, minus 0 second as the initial time. If you look at it, this is negative. Negative 0.98 minus 1 is negative 0.02 over 2 seconds here, right? But in chemistry, the rate of reaction is always positive. Okay, so it's always positive. So in this case, the negative here, you need to make it positive. So you add one more sign here as negative. So negative times negative is equal to positive. So now the reaction rate becomes 0.01 molar per second. So you added the negative here, the negative sign. So if you go back in our equation, yes, this negative sign here, that is the negative sign if we are referring to a decaying reaction, right? The concentration is decaying. So if you put negative sign, it means the decaying reaction. So the answer for R is still positive for this case because we just put the negative sign as a way of knowing that it is decaying, the concentration is getting lower. So in this case, we have the rate of reaction as 0.01 molar per second, which is basically the same with the rate of reaction for the product as well, because there are only one reactant and one product in this case. Now, if you look at another example here, because we are talking about reaction order, okay? So what is this reaction order? So if we have a reactant, normally, we have a few number of reactants like reacting two different chemicals, and then it will form into a product. So in this case, we have reactant A, and then we have reactant B. And then the A and B, the small a and small b here are all the coefficient of reaction, okay? So it's the coefficient, of the reactant. So we will not put values here for the coefficient yet. So we'll just put one here. So if we are looking at the effect of the changing of concentration of one of these reactants here. So let's say for example, we are looking at the effect of changing the concentration of A. What will be the reaction, or what will be the reaction rate, right? So we want to know what is the relation of changing the concentration of A to the reaction rate. So we will form the reaction rate here. And reaction rates are usually, you will get the values from the reaction based on experiments. So based on experimental results. So let's say we have these values here. So by making the B concentration as constant, so let's say we have 1 molar of concentration of B, let's make it constant because we are trying to see what is the effect on the changing of the A concentration. So let's change the concentration of A from 1 molar, 2 molar, and 3 molar. And then once you get the concentration, change the concentration, the initial rate, okay, of reaction is also you can get from the experiment. So you get 0.01 molar per second for 1 molar. For 2 molar, it becomes 0.02 molar per second. For 3 molar, it becomes 0.03 molar per second, while we are maintaining the concentration of B as constant, okay? So only A is changed. All right, so what effect of concentration of A on the rate of our reaction? So in this case, we can see from the results here from the experiments, if you look at this point here, from 1 to 2, from 1 molar to 2 molar, what happens to the initial rate of reaction? So from 1 to 2 molar, the increase is 2 times, right? 2-fold. So the reaction increases by 2 folds, from 1 to 2, 2 folds. The reaction rate, the initial reaction rate, is also increased by 2 folds, as you can see from here, right? So you can see here, the times 2 and times 2 for the reaction rate as well. So if you look at from 1 to 3, from here, from this side, from this side and this side, you can see that the initial rate is from 0.01 to 0.03. So what happens? From 1 to 3, there is an increase of 3-fold increase, right? So the reaction is 1 becomes 3, so 3-folds increase, and the initial rate also increased by 3-folds. All right, so now we question, so what is then the relationship of these two? When we increase the concentration, what is the relationship to the reaction rate? So look at this one. By asking that one, we will know that we need to understand what is n here. So what number shall we raise this to so that it will become or equal to 2, as equal as the relationship for the reaction rate that happens after we increase the concentration. So what number should we put here so that it becomes 2? In this case, it's 1, right? 2 raised to the 1 is 2. So it means the answer is 2. Okay, maybe so. And also in the same way, what number shall we raise 3 so that it becomes 3? The same thing, it's 1. All right? So in this case, we can say that the reaction rate in terms of relationship to the concentration A is proportional. The reaction rate is proportional. So this is the symbol for proportional, mathematical symbol, is proportional to the concentration of A raised to the n. All right? In this case, the n is equal to 1. All right? In this case, for this example here. All right? So in this case, we change this into mathematical equation. The proportional becomes equals, and then we add a proportionality constant. And this constant now is K. So K is the reaction rate constant now, as I mentioned in the previous slide. So from this equation, it becomes R equal K times the concentration of A raised to the N. And N is now the reaction order. This will determine, the N will determine in your equation if what is the relation between the concentration and the reaction constant. So let's say N. If N is equals to 0, what happens? What happens if N equals 0? So A raised to the 0 is how much? Is 1, right? In this case, A raised to the 0, any number, integer raised to the 0 is 1. So it becomes R is equal to K only. So R becomes K for an N equals 0, right? Okay. If we put N equals 0, R is equal to K, which in this case is what we call as 0th order reaction. Okay, and then we will discuss that one in the next slides. So going back, we can now get this formula here. All right. The negative here is just to show that the reaction is decreasing because we are talking about the reactant. Usually, the reactant is decreasing to form into a product. So that's why there's a negative. So the negative is just a direction for that. And C is the concentration, which is similar with what we have here, which is A in this case. And N is the order of reaction. Now, exponent or order of reaction order. All right. So now we will talk about that different types of reaction order. Okay. Probably I just mentioned this one from our original equation. The change of concentration in the control volume or accumulation is equal to the mass flux in minus the mass flux out plus minus RV. As you can see, there's RV because V is a volume and R is in terms of moles per second. All right. Or molar per second, molar per second, sorry. So molar means moles per liter. All right, so moles per liter, so molar is mole per liter. So if you have mole per liter and you have V here, volume, so you can cancel out the liter. So it becomes mole per second, which in this case is mass flux. So the mole can be converted into kilograms or grams, then you have a mass flux. So it's basically we have the same units for all here. So this is now the official equation for the mass balance with reactions. There are basically many reaction orders, but in most cases, there are three that we are referring here. So we have the zeroth order of reaction, okay? So with zeroth order reaction, which is R is equal to dC equal over dt is equal to negative k c to the n, where in this case, the n is the reaction order, so it becomes 0. So now it becomes 0 here. So now this one becomes, this one becomes 1. So c raised to the 0 is 1, so R is equal to negative k. So what can you see from this equation? In this equation, it means that the reaction rate, okay, the reaction rate of a zeroth order reaction is not dependent on concentration, or is it independent of concentration? It doesn't matter. Big concentration, small concentration, the reaction rate is constant. It's the same. It doesn't change regardless of the concentration. So you can see from this graph here, okay, from this graph here, this is the rate. You can see the rate from here, and this is the concentration. So rate versus concentration. So the higher the concentration, so it means from this part here, is the higher the concentration, the rate of reaction is constant. It stays the same. All right? It's very constant here. So it doesn't change regardless of the concentration of the reactant. So the zeroth order then does not vary with increasing or decreasing reactant concentrations. All right. For first order reaction, so based from the still equation of reaction rate of reaction, so now the n becomes 1, so minus kc. So what can you see from here? From this equation, R is directly proportional to C, to the concentration. So it means, what does it mean? It means that if you increase the concentration, the R will also increase the same way. So that's why we have a linear, it's a linear relationship. So you can see from this part here, okay? You can see from this part here, the green one is the first order reaction. So it means that this is concentration, this is the rate. If you increase the concentration, let's say from this part to here, higher concentration, the rate of reaction is also higher. At this point here, higher concentration, the rate of reaction is also higher. So there's a directly proportional to the concentration of the reactant. Okay, so that's why this is the first order reaction. The rate of loss is constant. It is dependent on the concentration. So now we will talk about the units here. Let's talk about the units here. What will be the units for the zero order reaction? I forgot to say that one. So what is the units for zeroth order reaction? So if you look at this part here, okay, so this is 1, and the zeroth order is a units of molar per second, okay? Molar per second, because we have the concentration here, all right? Concentration per second. So basically it's just the unit of the C, which is 1 already. All right, so it becomes molar per second for the unit of zeroth order of reaction. But in terms of the first order reaction, what happens there? The first order of reaction. The first order of reaction has a unit of 1 per second. All right, 1 per second. Why is this so? Okay, I think I will give you more of that details, how to get the units in the next slide, so it will be easier for the explanation, because I have some slides in the next slide. So this is 1 per second for the unit of the first order reaction. Now, for the second order reaction, what does it mean? So the second order reaction is also dependent on the concentration of the reactant. So in this case, if you look at the formula, the equation here, the rate of reaction is equal to negative kc raised to the n. And n is 2, okay, squared. So it means that the rate is actually increasing with the increase of concentration. In this case, I'm talking about 2 reactants, but it could also be according to 1 reactant. But the higher the concentration, the rate of reaction also increases. So you can see from here, in this slide here, the higher the concentration, the rate of reaction also increases. Special cases, in many environmental systems, the zero order reaction and the first order reaction are the usual reactions that are happening. So examples of the first order reaction are degradation of organic contaminants in the environment, or settling of contaminants on like absorption on particulate matter. So this is a first order reaction in most cases. All right. So let's go towards the explanation of other units here. So now this is the different units of the reaction order and their expression. So remember, when we talk about the reaction rate of constant, this part here, depending on the reaction order, you have different units. All right. So how to determine what unit of K in various reaction order? So we can use this kind of formula here. All right, this formula here can determine what kind of reaction we are talking about, or reaction order we are talking about. Okay, so M stands for concentration, 1 minus N. So this is a general formula to determining the units of reaction constant. So 1 minus N, which is the reaction order, times T to the negative 1. So this one means that M 1 minus N over T. Is the meaning of that one. So if you want to determine the K unit, what you do is put out the N. So what is going to be the N here? Example, N. Let's say we put 0. So N, M 1 minus 0 over T. What happens? So M 1 minus 0 is 1. So it becomes M over T. So this part here, M over T, so it's basically the concentration over time, so molar per second. So this molar per second, we put 0 here as N. So it means that this unit, molar per second, is the unit of zero order reaction because we put 0. All right? So if you want to put 1, for example, M 1 minus 1 over T, what happens? 1 minus 1 is 0. So it becomes M to the 0 over T. So this one, it becomes 1. So now you put 1 here as N. So N, this is the first order reaction. So the unit for first order reaction is 1 per second. All right? You can see from that, 1 per time. So that's why you can easily see the units of various orders. So let's say 2. So M 1 minus 2 second order over T, it becomes M raised to the negative 1 over T. So what happens now? So it becomes 1 over M over T, right? So 1 over M over T, so which is the same as this one. 1 over molar per second. So this is now the unit for the second order of reaction. All right. So if you have the summary for this one, there's an example here. If we triple the concentration of reactant A, what happens in various orders of reaction? So in this case, if we triple the concentration of reactant A, what happens to the zero order of reaction? Doesn't care, right? Doesn't matter what how big your concentration is, the reaction rate is constant. So it doesn't matter, it's 0. So change in rate is 0. There's no change in rate for zero order. But if we triple the concentration of reactant A in the first order, what happens to that one? It's 1. It's the square of that concentration. So it means that well, not square. It's the same amount or the order of increase as well. So if we triple the concentration, the change in rate will also triple. All right. For the second order is the square of that concentration. So if we triple the concentration, so if we have 3 here, okay, 3 molar, then the factor of the rate of change in the reaction rate will also a factor of 9. So it will increase quite high for this case. All right. So please remember the relationship between concentration and the reaction rate based on the various reaction orders. All right. So these are important here, and we will be giving some examples on how to use that one. Now, so let's input now the formula for the reaction rate. So in this case, is the mass balance formula. Then we have the reaction rate here times the V to make it all in mass flux. For steady state condition, if we have a steady state condition, this becomes 0 here. And so we get minus KCV for a first order reaction. All right, so it becomes KCV, first order reaction. So if it's a 0 order reaction, so it becomes 0 order reaction, 0 order. What happens? All right, so the C will be out, so make minus KV. All right, so it will be the 0 order reaction for that one. All right, some examples of that one. Where do we get this kind of reaction? It could be mainly in tanks. So we can see a lot of tanks and some containers in many environmental processes. So we usually have that one, or in pipes or tubes. All right, so this quite long aspect ratio. So the pipes are like this. So we can get some reaction inside, or the tank is like just a tank, or a sort of a container. So there we can input something inside, we can output something outside here, or you can just leave the tank on its own. So you can put inside here and make some reaction going inside, just steering. All right. So these kind of processes are what we call as reactors. Okay, the container, the place where reaction is ongoing. So that's are the reactors here. So we can have some continuous reactors, or there's a continuous process wherein there's an input here and there is an output going out. And we can also some good as batch reactions. It means that you just put something inside and leave it there, react, and then after reaction, after we get the reaction that we want, we can just put it out and then replace a new one and then react again. So this is a batch by batches. All right, so what we call as batch reaction. So this reaction more or less is a transient state. So transient because once you put the chemicals here, then the reaction changes, the concentration changes inside the tank, right? So it's not yet at steady state condition. So it becomes changing of the concentration through time. But if you look at some continuous reaction like this one here, where there is an input, there's an output, we can say this is a steady state condition because you are constantly putting in mass and putting out mass. All right. After some time, the steering here inside the tank will become, steady, and the accumulation becomes constant or zero. I mean, so zero. So there is no more accumulation. It becomes more or less a steady state condition. So we will discuss these types of reactors now.